next presentation, because our speaker is going to continue on with his next talk, which will be on stateful multi-pipeline programmable switches.
Yes.
So state is the question here. Please.
Can we get the... All right. Yeah, so this is slightly different. So in this presentation, what I'm going to do is I'm going to start with a motivating example. Okay? So let's consider a packet processing program. Very simple. So you have a switch that maintains packet counters for, say, each destination IP, right? And if the counter value for the destination D exceeds the threshold, switch simply drops all subsequent packets destined to D. So this is what you would call a stateful packet processing program. Why is it stateful? Because it's maintaining a counter state on the switch. Okay? So suppose I gave you this program, and I told you to, hey, implement it on Tofino or using P4 or whatever. So what will you do? Well, you will open up P4, write the code. It will take you, a few hundred lines of code. And then you would expect it to be compiled onto a switch pipeline. And maybe it won't look exactly like this, but it would look something similar to this, right? You will have some hashing going on. Then you have your state there. And then you do the check in the end. At least that's what you would expect, right? And then if the packets arrive at the runtime, what will happen? Well, you get a packet with destination value X. It will be hashed. You get the index. You go to that index. You increment the counter value. You carry that counter value in your metadata. And then you check whether that counter value is over the threshold or not. If it is, drop it. If it is not, don't drop it. Perfect. Easy, right? Well, obviously, no. It's not that easy, because this abstraction that you have of a single switch pipeline is far, far away from the reality of the hardware. So the hardware actually looks something like this. So it actually has multiple parallel pipelines running in parallel. And this is really needed because the clock speed of a single pipeline has kind of saturated. So if you want to go to multi-TBPS line speeds, the way at least Tofino does it, or most of the programmable switches do it, maybe not the Juniper one that we discussed earlier, but definitely the way Tofino does it is it uses multiple parallel pipelines. Now, the key here is the second point. The way it's implemented right now on these switches, each parallel pipeline processes packets independently. So there is absolutely no coordination going on. So actually, one way to view it is you actually have 4 programmable switches inside a single switch if you have 4 pipelines, because they are all just independent. You can pretty much program them independently with different programs if you want to. So that's kind of an issue. So what is the goal here? So the goal here is that, well, from programmer's perspective, we still want the programmer to have this logical single large pipeline abstraction for the ease of programmability. We don't want to burden programmers with all the parallelism and things like that, right? They just assume that, hey, I have a large single pipeline that's running at rate R, and I will write my P4 program against this. Perfect. But what we want to do is, under the hood, we want to be able to map that program that was written for one large pipeline and automatically map it down to these multiple smaller pipelines that are running at much smaller rate than the large pipeline. And the way we want to do this mapping is we want to preserve 2 kinds of equivalence. So we want to achieve functional equivalence, very important. We want to make sure that the runtime behavior of the program on this set of pipelines is similar to if that pipeline was just one giant pipeline. So this is important. And secondly, we also want to achieve performance equivalence, but that is a second-degree objective because we want to achieve performance without violating the functional equivalence. So we want to get as close as possible to line rate, but without violating functional equivalence. So the first-degree goal is to maintain functional equivalence. Okay? So that's the overall goal of this paper. So the contribution here is going to be a new system called MP5, which stands for Multi-Pipeline Packet Processing Pipeline, which is going to extend your current programmable switches architecture, compiler, and runtime, and it would guarantee you functional equivalence with high performance. So it's not going to guarantee you line rate, but it will try. It will try its best. But what it will guarantee is functional equivalence. under certain assumptions, which you can find in the paper, or you can talk to me. OK, so let's start with some naive approaches to solve this problem, right? And to make things easy, I'm going to start with a stateless packet processing program. So forget about stateful for now. Let's just focus on stateless, right? Easy. So here the program is that switch increments the TTL, time to live value, inside a packet header by 1 every time a packet arrives. And if this value exceeds some certain threshold, you drop the packet. Pretty standard operation inside most of the switches. Now, this is different from the previous example because this is stateless. Here, the switch is not maintaining any state. So again, you write a FIFO program, and this time it will be compiled something similar to this, right? That's good. But hey, you have 2 pipelines here, right? So you want to utilize the full bandwidth of those 2 pipelines. So how do you do that? Very simple. I'm just going to replicate it. I'm just going to replicate this exact program on the 2 pipelines. And that's it. Done. You can achieve functional equivalence and performance. You can run things at line rate. It's guaranteed to give you functional equivalence. All is good. OK? But now let's look at a stateful one. Right? Now, this is where things are going to get a little bit tricky. So suppose we go back to our original stateful packet processing program, and we try to do the same thing here as well. So here also, we just blindly replicate our program on both the pipelines. Now, it's easy to see that this might not always work. For example, if, say, you have 2 packets arriving, both with the same destination, they are going to independently increment the index 1 to 1. That's not functionally equivalent to a single pipeline switch. If it was a single pipeline switch, that value would have been 2, not 1. Right? So clearly, this is not going to work. So this violates functional equivalence. Now, at this point, some of you might have, especially those with architecture background, might have this question that, hey, this kind of looks very similar to cache coherence problem in CPUs, right? And we have solutions for that. And actually, it's true, yeah. In principle, you can actually implement a cache coherence protocol inside your programmable switch, and that might solve the problem. The only issue there is that you have to realize that the performance constraint of programmable switches is far more constrained than for the CPUs. So for example, if you try to implement protocols like MESI, which is a classic cache coherence protocol, it involves all sorts of state machines, and it's very hard to achieve line rate if you try to implement it here. So we want to avoid that. So let's look at a less extreme option that gives you functional equivalence. What about, forget about replication. I'm just going to limit everything to a single shared pipeline. And suppose somehow we can steer all packets to that shared pipeline. Obviously, this is going to solve the problem, but it's going to also limit your stateful processing. So it gives you functional equivalence, doesn't really optimize for performance. So you get one, not the other. We want both. So this is where we are. So you will see this table multiple times during this presentation, and this will tell you where you are currently in the presentation. So here we are currently. So you have these 2 techniques, and using those 2 techniques, you can achieve functional equivalence for stateful operations. Performance is still an issue. So that's what we'll try to solve next. So how to improve performance without violating functional equivalence? And really, the crux here is this shared state, right? This is the question, that how do you store the shared state that enables high packet processing throughput? We have already seen one, or basically a couple of examples, where you replicate the entire thing. That doesn't work. You put everything in one pipeline. That doesn't work. So why not do something in between? So basically, what we can do is we can shard it, right? So sharding is different from replication. So here, you have only one copy of each state, right? When you are replicating, you have multiple copies. So if you shard the state, then for certain workloads, this is going to give you better performance, because now if you have packets coming in that are accessing different states that are sitting in different pipelines, now you can process them in parallel, right? That is good. So this is the easy part. The hard part is, what is the optimal sharding strategy, right? For example, if you had, say, this packet pattern, where you have blue packets and red packets, and blue packets access the blue state, and red packets access the red state, which is index number 3, then you can argue that, hey, this is the optimal sharding strategy, because you can process everything in line rate. 50% of packets are blue, 50% of packets are red. Everything is great. But if you change the traffic pattern to something like this, where green packets are accessing index 2, red packets are accessing index 3, now, if you do this and run it like as it is, this is not optimal. This is going to give you half the throughput. However, if you somehow rearranged it something like this, then again, it becomes optimal. So the point I'm trying to make is that what you really want is to ensure that the state axes are uniformly distributed across pipelines. That's really the goal here, so that one particular pipeline doesn't become a bottleneck. The problem is that it is hard. It is hard to predict, basically, in advance, because this really depends upon your packet arrival pattern. So just sharding the shared state doesn't do it. What you really need to do is you need to be dynamic about it. So you need to somehow monitor the state access patterns at runtime and try to periodically reshard things across pipelines to make sure that your performance is met. So this is what we do. The only problem is that if you try to solve an optimal version of this problem, it reduces to a variant of bin packing problem, which is NP hard. So what we end up doing is we end up using a heuristic that approximates bin packing, and that is amenable to fast hardware implementation, because that is key. OK. So there is one missing detail, though. So the missing detail here is that what happens when packets arrive on different ports and the state that they want to access is sitting on a different pipeline. So this is something that we did not discuss, right, so far. So what do you do here? In fact, you can just generalize it. For example, a packet might be accessing multiple different states, which can be sharded arbitrarily. And so the packet might have to go back and forth between multiple pipelines. That could very well happen, right? So how do you solve this problem? So let's first try to solve this problem without making any hardware modifications. Let's not try to make any hardware modifications. Let's say we have a vanilla Tofino switch, and we want to solve this problem using that. So how do we do that? Well, there's this thing called packet recirculation. So that's what we're going to do. So how does this work? Well, this packet will come in. It will access the state that it wants to access. And then it will be recirculated all the way back to the second pipeline to access the state that it wants to access there. And then it will be again recirculated back to the third state, right? So this solves the problem, but, well, not quite, right? Because the problem here is that it results in a huge throughput penalty and also increased latency. And the fundamental reason for that is because packets are revisiting the same stage multiple times. And in fact, in the paper, we discussed that the performance of this could be even worse than the naive approach, where we put all the stateful stage in a single pipeline. For certain workloads, this could be worse, depending upon how many recirculations you do, right? So this is not good. So what we really want is really a feed-forward only packet sharing design. We don't really want to revisit states over and over again, OK? So let's see how we do that. So if you look at the current switch design, this is the abstraction of the current switch design, right? So a packet in stage I of pipeline J could move to a stage I+1 of only pipeline J. That's what your current switch says you can do, right? And we have seen the issues with that. So what we are going to do is we're going to change it slightly. So we are going to modify the hardware, and we are going to allow packet in stage I of pipeline J to move stage I+1 of any of the pipelines. And the way we are going to achieve it is very, very simple. Many of you would have already thought we are just going to use a crossbar. Now, obviously, this comes with higher wiring complexity compared to the previous design. But the key here is that if you think about these pipelines, right, we only have a handful of these pipelines. Or at least we hope that we will only have a handful of these pipelines, at least in the foreseeable future. So this is what allows us to limit the overheads of this wiring complexity. And you can see the evaluation results in the paper. All right, this is great. So back to the question, right? How to improve performance without violating functional equivalence. And turns out that after applying all these techniques, we get rid of this one, the second one, not needed. Instead of that, we do these two things, and we have better performance. But what about functional equivalence? Did we somehow inadvertently violate it? And turns out we did, actually. So to show that, I'm going to take this example. So before I go into the example, what I'm going to do is I'm going to establish something. So suppose if you had a single pipeline, right? By the way, these are all color-coded. So packets in red axis, red state, packets in green axis, green state, and packets that have both red and green axis, both the state. So on a single switched pipeline, it's always going to happen that D will access the state green before E, because that's the abstraction switches give, right? If packets come on the same port, they're always going to be processed in the order. But turns out that this could be violated here in this scenario. For example, A and B comes in here in time slot 1, then D and C come in, then E comes in, and now you have an issue. And this packet preordering can also impact application performance if D and E belong to the same TCP flow. So how do we avoid this? So what we try to do is we try to enforce ordering preemptively. So the point here is that if you wait for the packets to reach a stateful stage, it's already too late, because those packets now can be queued in any arbitrary order, and it's not going to work. So you try to do it preemptively. And this happens in 2 steps. First step, you try to preemptively figure out all the states a packet would access, which is hard in general, but the insight that we use is that for most packet processing programs, it's actually not that hard, because they just use kind of hash of the subset of packet headers to figure out what index they want to access. And this can be figured out easily.
Which means that we need to come to an end.
Oh. OK, so I'll just skip this. Yeah, you can look into the paper for more details. And the idea is basically we have this preemptive state access enforcement that gives you all the properties that you want. And what we show here is that for realistic workloads, you can achieve both line rate and functional equivalence. And this is the summary. We wanted functional equivalence and performance equivalence. We proposed MP5. It has 3 characteristics. It uses a crossbar, it dynamically shards state, and it uses a preemptive state enforcement access order. Thank you.
Are there any questions, guys? Jen.
Hey, Jen Rexford, Princeton. Really nice talk. I'm just curious if you thought about small relaxations of functional correctness, particularly in settings where the operations you're doing might be commutative and associative. And I'm sure you've thought of this. I'm just curious what your thoughts are.
That's a very good question. Yeah, so I haven't really thought about it that much. So I wanted here to build a general design that would work for all scenarios. But you are very right. For example, even the example that I showed, it kind of uses a commutative operation, right? So there you may be able to periodically synchronize state or add things and do something like that. However, that would not work if those operations are non-commutative, right? So yeah, so this is like a good future work.
Steffen Smalka from Google. Thanks for 2 amazing talks. I have a small technical question. So if packets can jump between different pipelines, do you need some kind of scheduling, or how do you deal with that?
Right, so what we don't need is scheduling, what we need is routing, basically, right? So essentially what happens, so this is something that I had to skip due to time. So what I was going to talk about was that we have this preemptive state order enforcement, right? So this is something that is added at the front of the pipeline. So as soon as a packet enters, you already know what states that would access. So you can just encode that information in the packet header, and the packet will be routed accordingly.
So what happens if you get any conflicts?
Right, so you won't get any conflicts because we use, well, you can get conflicts, and in that case, the packet would basically be buffered in that pipeline.
So you need additional buffering then?
Yes, we do need additional buffering.
So what is the cost and the overhead of this?
So the additional buffering, at least in the evaluations that we ran for realistic workloads, for each stage, a FIFO of size maximum 11 packets was sufficient. Now, remember here, packets are not full packets. These are just headers. So 11 headers, basically.
Jacob Schröder, Marvell Technology, not the trainers Marvell. So I was just thinking this routing of packets between your pipelines, that seems extremely expensive. Wouldn't it make a lot more sense to have a single shared counter resource that all the pipelines would share, and then you would just do some statistical increase in bandwidth there?
Right, so the other alternative could be that you use some kind of a multi-ported memory, for example, right? So you use a multi-ported memory, store it in one of the pipelines, but then you will have to basically scale the speed of that pipeline to whatever number of pipelines you have, right? So if you could do that, then yes, that would work. But scaling the clock speeds was one of the motivation why people actually have these multiple pipelines.
You certainly need multiple pipelines, no doubt about that. I was more thinking about, instead of scaling the speed of each of these memories, counter memories, then just distribute across, say, 8 memories, and then have 1/8 of the counters in each, and you do statistical distribution on them.
So what is the statistical distribution that you're talking
It
about?
means you have 1/8 of the counters in each of them, and then on average you would have less load on each.
Right, so...
Okay, guys, this sounds like you want to actually a comparative evaluation, which you guys take offline. So thanks again to the speaker here.